And what I want to do is just spend a few minutes going through some of the stuff you need to know for our current work. We will practice balancing some chemical equations as we go. So if that's something you're still working on figuring out, this is a good opportunity for you to see some practice for that. So we're talking about chemical equations, and we need to be able to recognize formulas and name them, and look at names and write down the correct formulas for them, because that's using the language of chemistry that we worked on so hard. All right, so you guys should have your ions reference sheet and your periodic table handy. If you don't have those on paper form, you can always just click on the links on the announcement I made about this just now so that you could join. And those will be handy so that you can use them to identify things and remember how to name things and so on. I want to go through all the formulas and names that I'm going to use, just so we know them in advance. Then what I want to do is write down some equations using descriptions in words, and then write down descriptions in words from chemical equations. And then once I've finished doing the sort of basic lesson, then I'm going to open it up for you guys to turn on your audio and video and ask me some questions if you'd like. Okay, so first of all, we're going to be looking at these chemicals. We've got three categories: elements, molecular compounds, and ionic compounds. And among the elements, we have hydrogen, oxygen, nitrogen, and chlorine, which are all nonmetals. And many of the nonmetals, not all of them, but many of them appear always as their smallest particle, having 2 atoms each. Diatomic molecules, we call that. But things like sodium, which is a metal, never do that. They always just have the 1 atom in the formula that we write down for that. For the molecular compounds, all of these have common names, except for carbon dioxide, which I guess its common name is the same as its systematic name, where you name the elements and you use prefixes, unless it's a 1 for the first element, but you use prefixes to tell the number of atoms. This is not dicarbon hexahydride, although that would be a good start. It's called ethane. This is called ammonia. That's called water. Okay, for things that won't be obvious to you as far as the names, I'll always give them to you, so don't worry about memorizing a lot of names. We have a couple of ionic compounds that we'll see in some of the chemical equations that I'm going to go through. One of them is potassium chlorate. Another one is potassium chloride. And the last one is sodium chloride, which we may be familiar with. All right, so those are all of the chemical formulas and names of everything that we're going to look at today. Now let's talk about using a description in words, like a story of a chemical reaction, to write down and then balance a chemical equation. So hydrogen gas and oxygen gas combine to form water vapor. Okay, so the fact that it tells us the state of matter is important. It helps us to recognize what's going on and be descriptive. So hydrogen gas, hydrogen is H2, never just H, and oxygen is O2, never just O. Okay, so it's important. If you see this written in words and you don't have something like this in front of you, you need to know these ones, right? There are 7 that were diatomic molecules, right? And then it says to make water vapor, to form water vapor. So vapor is another word for gas. It's just kind of, we use the word vapor whenever we're talking about a material which is like normally a liquid, but it's in the gas phase, right? Whereas these are pretty much always gases. You can liquefy them, but anyways, they're generally gases. Now that we've got the equation written along with the state of matter in this little parenthesis after each formula, then we can balance the equation. And the way to balance a chemical equation, of course, is to make sure that you have the same number of atoms on both sides. So to make sure we do, we count them. On this side, we have 2 atoms of hydrogen in one molecule and 2 atoms of oxygen. On this side, we have 2 atoms of hydrogen, but only 1 atom of oxygen. So we need to make the number of oxygen atoms equal, and we're only allowed to do that by putting a coefficient in front of the molecular formula, or whatever the formula is, right? So that changes the oxygen to be the correct number, but it also forces us to change the hydrogen. That's okay. Don't let the fact that this changes cause you to change H2O into H2O2, or, I've seen even worse things than that. This is a different chemical than this. Sometimes people will put in subscripts like this, right? And they will change the formula into a chemical which doesn't actually exist. So you want to make sure not to change the formula. The formula identifies what it is. So you can't change the formula by changing the subscripts. Okay? So I'm going to just make a little note. Don't change these. Okay, so that does mean that we have an unbalanced hydrogen. So that means that we need to go over here and see what we can do. So if we multiply this by 2, that gives us a total of 4 atoms. And so now we have a balanced chemical equation. Okay, so that's the first one. I've got 4 more examples. 1 more where we start with words, and 3 where we start with the equation as formulas. So the second example is with liquid potassium chlorate. And it says it decomposes to form oxygen gas and potassium chloride. Okay, so liquid potassium chlorate is potassium ions and chlorate ions, where they balance out 1 to 1 because each one is plus or minus 1. And then potassium chloride is one of our products. Doesn't matter what order they're written in. I know I wrote oxygen gas first, but I want to write oxygen gas second here. It doesn't matter. Okay, it says this is liquid. That gets a little L. I usually write it as a cursive L so you can tell it's not a 1. And then we're going to make, this doesn't say, so I'm going to write down solid potassium chloride and gaseous oxygen. Okay, oxygen gas. So now that we've got the equation written, okay, you could call this like a skeleton equation. We want to count up all the atoms on each side and balance it. We've got 1 potassium and 1 chlorine and 3 oxygens on the left side. Got 1 potassium, 1 chlorine, but only 2 oxygens on the right side. So the rule is you always want to find the least common multiple, and you can only change the number of atoms by putting in a coefficient in front of the whole formula. You cannot change these subscripts. Like you just can't change this to a 3. This, when you heat it up in a test tube, it does not make ozone, which is O3. You can't just change it. Okay, but the least common multiple of 2 and 3 is 6. So to get 6 oxygens on this side, I just multiply the 2 by 3 to get 6. On this side, I'm going to multiply the 3 by 2 to get 6. Now, that does change everything in the molecule when I put a coefficient in front. So now I have 2 potassiums and 2 chlorines. All right, so, but that's pretty easy in this case. I could just put a 2 in front of KCl on the right-hand side, and I get 2 potassiums and 2 chlorides. All right, so now we've got a balanced chemical equation that matches with its description in words. Okay, now the next equation is written out as an equation using chemical formulas, and our task here is to write a description of it in words. Before we do that, let's balance it. We've got just nitrogen and hydrogen here. Okay, and so it's not balanced as it's written, and we've got 2 of the hydrogens on one side and 3 on the other. So again, we need a least common multiple of 6. Okay. Now, that does change the number of nitrogens here, but it makes it change so it matches. So it's actually kind of nice that way. Now, we need to write a description of this in words, and that can be a little bit more challenging than going the other way. But we know what the names of these things are. We looked at them on the other side of this piece of paper. This is ammonia. So we would just describe it using its name and its state of matter, like ammonia gas, or you could say gaseous ammonia. There's a lot of flexibility. Well, there's a little flexibility. And you could just say reacts, because it's just all by itself. It doesn't react with anything, but you could say reacts with if it has another reactant. So reacts to form, here, I'll switch it around, gaseous nitrogen. That's another alternative if it's a gas phase reactant or product. And gaseous hydrogen. So really, it's just a matter of naming everything in the equation and using some verbs and some descriptors to make it all hang together. Okay, so that's that example. And then the next example is sodium reacting with chlorine to make sodium chloride. It's a pretty common error that people do this. Right? Don't do that. That's not allowed. Sodium chloride has to be NaCl because it's Na plus and Cl minus. So they have to be 1 to 1. Right? So ions still have to balance their charges. And here, chlorine is not an ion. This is a pure element. All right? As a pure element, chlorine exists as pairs of atoms bound together to make these individual molecules with 2 atoms each. All right, so let's balance this equation. Okay, one sodium, so far so good. 2 chlorines, only 1 chlorine. Okay, so it isn't balanced. So we want to balance the chlorines because that's what's not balanced. We do that by putting a 2 there. This is the temptation, resist it. So that changes both atoms to 2 because we multiplied the whole thing by 2. But we can just put a 2 in front of just the sodium on the left-hand side, and that will work. Okay? Now, let's go ahead and describe this in words. Oh, I forgot to put this in. We'll put solid, and we'll put gas, and we'll put solid. So our description is solid sodium reacts with chlorine gas to make, so you can use the word to form or to make, solid sodium chloride. This is a very entertaining, explosive reaction, which you will never see me do in a classroom, but people have done it and they videoed it. It's on YouTube. One guy tried to make sodium chloride this way to salt his popcorn. He set the popcorn on fire. It's very entertaining. Not recommended. Don't try that at home. Anyways, so that's how you write out the name, the description in words. Okay, you just name each thing and give its phase of matter, and you say reacts with for the 2 reactants. And for the products, you just name those products, okay, after some appropriate verb. All right, let's do one more, and then I'm going to stop the recording. And as long as we are still recording, I think we are, it says we are, then I'll take some questions if you guys have them. All right, so let's go ahead and put in my states of matter, which I forgot to do, and balance this equation. So we have C, H, and O on both sides. 2 C's, 6 H's, 2 O's, 1 C, 2 H's, 2 plus 1 O. So we've got a total of 3, okay, and the 2 separate molecules. Oftentimes, if you have 2 molecules on the same side of the arrow that have the same atom in them, balance that element last. All right, so let's do the carbon and the hydrogen first. Okay, so we got 2 carbons, so we need to put a 2 here, okay? But that changes the oxygens, right? I'm sorry, that changes the oxygens on this side from 2 to 4. All right, so now we have a total of 5 oxygens on the right. Now the hydrogens, we've got 6 on this side, so we need to put a 3 in front of the water molecule to make us have 6 hydrogens. But that changes the oxygens, and now we have 7 oxygens. All right, now this one is one of those examples of an equation where people can feel a little anxious because it's like, well, I can't multiply this 2 by anything to get 7, right? I mean, you could, but it's you know, it doesn't, it's 3.5, right? You can't put 3.5. So what do? Well, again, least common multiple to the rescue. Least common multiple of 2 and 7 is 14, right? They're both primes, so you have to multiply them together to get their least common multiple. All right, so that means I need to have 14 atoms of oxygen on both sides. So the way to do that is to put a 7 there. That's easy. But on this side, in order to get 14, I have to double this number. So the easiest way to do that is to double both of these. So get out your eraser or cross it out. I don't care if it looks messy, as long as I can read it. Doesn't really matter what it looks like. We're going to change that to a 4 and that to a 6. Okay, so we'll double both of them. So this is 8, and that's 6, and that makes 14. Now, that does change the carbons and the hydrogens, but not in a way we can't handle, right? We just kind of keep going until it's balanced. We've got 4 carbons. Oh, we can get 4 carbons by multiplying this by 2. We've got 12 hydrogens. Well, if we multiply this molecule by 2, we've already got 12 hydrogens. So it works out. All right, so that's some examples of writing and balancing equations. I almost forgot. We need to write out an equation, a description of this equation in words. And we could write it like this. Ethane gas. Now, this is a combustion reaction. Sometimes we use verbs, although you could just say reacts with oxygen here. Sometimes we use verbs that are more descriptive. Ethane gas is a fuel, okay? It can be burned. So ethane gas burns in the presence of oxygen gas to form gaseous carbon dioxide and water vapor. Okay, so this whole phrase, burns in the presence of oxygen gas, you could have written instead, and this is fine, reacts with oxygen to form. Okay, we could read it that way, and that's fine. I'm not asking you to memorize a specific way to write the equation out in words, but to write out a description that's appropriate. All right, so that ends the lesson that I'm going to record. And provided nobody's names appeared in the recording, I'll post this on the classroom for everybody else. All right, so I'm going to stop recording.